So last time we ended up briefly talking about the spectral decomposition of symmetric matrices. I don't want to spend too much time on it. It's important, and there are more details on some of the previous lecture videos. So just to briefly, again, remind you what it is, it's that every symmetric matrix has a decomposition. It can be written in this factorized form, where these U and lambda matrices are related to eigenvectors and eigenvalues of the matrix. So the columns of U are the eigenvectors of the matrix, and the diagonal elements of lambda are the eigenvalues corresponding to those eigenvectors. So for example, if you look at the first column of U, that would be the eigenvector corresponding to eigenvalue lambda. And then you have the second column, which is U2, that would correspond to this eigenvalue. So what that means is that A times U1 is lambda U1, A times U2 is lambda 1 U1, lambda 2 U2. So each one has its own eigenvalue. And these eigenvalues could be repeated. So lambda 1 could be equal to lambda 2, but U1 and U2 will be different. So the point is that for every symmetric matrix, you can find a full set of, let's say, orthonormal eigenvalues in the sense that they would span the entire Rn. So this is an n by n matrix. So we're talking about square matrices. So there are n vectors each in Rn, and they form a basis, so they can't be repeated. So if U1 is equal to U2, for example, this is not going to be a basis. Anyone remembers what would be wrong in that case? So if I have repeated eigenvectors here, can that set of vectors be a basis for the space for Rn? Just to check whether you guys are awake.
Linearly dependent, so no?
Yeah, so they're not going to be linearly independent. Yeah, so part of this is that even though all the eigenvectors eigenvalues could be the same, or some of them might be the same, these eigenvectors are all going to be different. That's the part of this theorem, that you can find a set which is linearly independent. Moreover, you can actually make them orthogonal. So you can make them pairwise orthogonal. So different eigenvectors, so different columns basically are orthogonal to each other. So for example, U1 inner product U2 would be 0, U1 inner product U3 would be 0, U2, U3 would be 0, and so on. And you can also make them unit norm. So the norm, if you go back to, let's say, the slides we discussed a couple of, maybe 2 lectures ago, maybe the last lecture, the norm is well defined, and the norm can be made to be 1. That's easy to do for every vector. You can always normalize it to unit norm by dividing by its norm. So that's the, yeah.
Why do we normalize it? Why do we normalize it? Like, what's the logic behind it?
It has a lot of useful features. So if you don't normalize it, you're not necessarily going to be able to write it in this nice fashion. Let me remember if it's possible to. You still can write it, but it would be a little bit more. I would say it wouldn't be as clean. So I believe so. The eigenvalues, this diagonal would have like the norms of these on them as well. So this nice way of writing, so separating this into a matrix that has only eigenvectors and one that has only eigenvalues. This can be achieved by this procedure. So for example, if I have a set which is only orthogonal, so suppose I have V1 up to Vn. These are orthogonal. So an orthogonal orthogonal basis of Rn, all of which are eigenvectors, I can get an orthonormal basis like this. I can divide each one by its norm. You can easily argue that each one still is an eigenvector. This is a number. And the orthogonality still holds. And now it's like, this is going to be an orthonormal basis. So then we have this representation. I can think of this as U1. We have this representation for this, and you can see what the representation will look like in terms of the original V's. So I'm gonna maybe let me try to maybe do it a little bit more. Add here. Add here. Add here. Okay, so if you look at the original one, so A is U lambda U transpose. This can be, so if U is like U1, these are the columns, U2, UN, and then lambda is lambda 1 up to lambda n. It's not hard to see that this can be written as summation I. You can expand it. This is a good exercise for you to do this. You can expand it as like lambda I, UI transpose. These two are equivalent. This is just a property of matrix multiplication. So if you do it via the column expansion of U, you would get something like that. So if you agree with this setup, and if you believe this is true, then you can write this, if UIs are like that, let's say VI divided by norm VI, then this representation would give me that A is equal to summation. If you expand, you would get lambda I VI squared. These are constants that come out, and then you get VI transpose. And if you put it back in matrix form, this would look like V lambda tilde V transpose, where V would be similar to you. This is like has columns V1 up to Vn. But now lambda tilde would be like diagonal elements would be this. This is still fine, but you can see it doesn't have that nice feature that you separate the eigenvalues and eigenvectors. So this also has something about the eigenvectors in it, which is the norm of the eigenvectors. But still, this is useful because there is some sort of diagonalization. The other aspect is that once you have an orthonormal basis, then U transpose would be the inverse of U. And this also simplifies a lot of things. With V, it's not going to be like that. So if you do VV transpose, I encourage you to try to do it. It's going to be diagonal, but it's not going to be identity. So the inverse is not V transpose. Right, so does that answer your question?
Yeah, it does. Thank you so much.
Yeah, no problem. It's just very convenient to do it this way, especially in like abstract arguments where you don't necessarily care about the internal sort of vectors. You just need these properties that U. So just remember that U is an orthogonal matrix. U being orthogonal is equivalent to the columns being orthonormal. If they're just orthogonal, then U transpose, these would be, wouldn't be, identity would be just diagonal, which is not, I would say not ideal. Okay, any other questions? That's a little bit more actually than I wanted to talk about, but feel free to ask questions if it's not clear, or you could go over the videos and slides, Wikipedia, like other resources, and if you have questions, let me know. My guess is that usually you don't see it presented in this fashion, maybe in the early, like an introductory linear algebra course, maybe you do, but usually you learn about eigenvalues and eigenvectors, but the fact that this leads to this decomposition is very useful for symmetric matrices, that such a decomposition exists for every symmetric matrix. It's a little bit more than just eigenvectors and eigenvalues. I mentioned that the eigenvalues could be all the same, but still you can find the orthonormal basis. So here are some examples, and once you have this representation, you can read a lot off of it. So one thing that you can read is the eigenvalues of the matrix. So the eigenvalues would be these diagonal elements. Usually you calculate these when you try to compute the SVD, but because these matrices are orthogonal, a lot of the properties of A and this diagonal matrix are the same. So for example, rank of A and rank of lambda would be the same. Some other properties are the same. So it's easy to figure out the rank of a diagonal matrix. Anyone knows how to determine the rank of a diagonal matrix? What would be rank of A1 and?
It would be 2 for A1.
2 for A1 and
1 for A2.
Right. So why?
Because there are 2 pivots in A1, like 3 and -1 are the pivots, and in A2 they are linearly dependent. So there's only 1.
Right. So if you want to be like simpler, so for diagonal matrix, how to determine in general the rank? I give you a diagonal matrix. What is the rank? I see someone in the chat, but maybe would you want to say it loud?
Oh yes, like we just look at the non-zero diagonal entries.
Right. You look at the diagonal entries and count the number of non-zero elements. That would be the rank of the diagonal matrix. It's really simple to argue that. Try to argue for yourself from the first principles. So this is like the dimension of the column space, or the maximal number of independent column vectors. So the rank of this is 2 because there are 2 non-zero elements. The rank of this is 1 because there's just 1 non-zero element. So that's one easy consequence. There's another sort of consequence is that's related to the thing that we want to talk about later, just in a few seconds. But any other questions here? Okay, so the other property that they share is this positive semi-definiteness. So has anyone gotten a chance to go over this? Anyone knows about PST matrices or learned about PST matrices? Positive semi-definite matrices. Yes, so what is a positive semi-definite matrix?
Yeah, like you wrote there, like it just like for all x, then the inner product of x and ax is non-negative. Yeah.
Right, so this makes it easy. Yeah, a symmetric matrix is positive semi-definite if exactly this holds. So this inner product x and ax, which can be written as x transpose ax, is a scalar, it's a number, and you want it to be non-negative for all x in Rn. If it turns out that this is strictly positive for all x that are non-zero, then A is positive definite. So this is a property of symmetric matrices, and this is the definition, and this is also the definition of positive definiteness. So semi-definite means you allow equality here. Definite means it's strict unless x is 0, which is trivially 0 in that case. So this is the definition. There are sort of characterizations in terms of eigenvalues. So for any symmetric matrix, the eigenvalues would be real. So they won't be complex numbers. And a symmetric matrix is positive semi-definite if and only if all the eigenvalues are non-negative. And it's positive definite if all the eigenvalues are strictly positive, no zeros. So for example, this matrix is not positive semi-definite. It's symmetric, but the eigenvalues, the eigenvalues of the diagonal matrix are just on the diagonal elements. So these one of them is negative, so this is not positive definite. And this is positive semi-definite, but not, so PSD, but not PD. This is not PSD even. And you can see that being positive semi-definite is shared between A and its diagonal representation. As I mentioned, it's based on the eigenvalues, and you can see that the eigenvalues are just the things that appear here. And it's easy for a diagonal matrix to prove that the diagonal matrix is positive semi-definite if and only if all the diagonal elements are non-zero. So in any case, once you have this, you can read the rank, also read whether it's positive semi-definite or not. It's harder to see from this that this is not positive semi-definite. This looks like it might not be positive semi-definite because it has negative elements, but it's this is not a problem. So a positive semi-definite matrix can have non-negative elements, okay, as you can see here. So it matters that the eigenvalues be non-negative, which is true. And it turns out that this also satisfies this definition. So this definition is a little bit tricky. This doesn't imply that elements are non-negative. It's more subtle than that. And in fact, you can use this spectral decomposition to prove this, that the PSD matrix A is PSD if and only if the eigenvalues are non-negative. If you're interested, try to prove this using the definition. Try to prove this using the spectral decomposition. But you're not going to worry about. These are just properties that you can remember. But it's also easy to try. Any questions? So exercise. Try to prove using spectral decomposition. And the definition of positive semi-definite matrices. Questions? Okay, so one last point.
Oh, wait.
Yeah.
No, I just have a confusion about the positive definite. I kept staring at the positive definite above, and I was kind of confused about how you found that specific positive definite.
Are you talking about the example or the definition?
Yeah, in the example.
So yeah, which one? This second one? Yeah, the first
yeah,
one.
the second one and the first one. Like, how did you get 3 and 0 or 0 and -1 in these cases?
Oh, this is not related to the positive. So this part, the fact that you have this is the spectral decomposition. You have to do the eigenvalue, calculate the eigenvalues and eigenvectors. Is your question is that how I write?
Yeah, how you arrived there.
Right. Okay. So that's an exercise for you. You can also try to. I don't think I ever do it in one of the homework. So try to do this. You have to compute the eigenvalues. So compute.
Oh, okay.
The eigenvalues of A1, and then the eigenvectors. So eigenvalues, when you compute them, it will be these. And in the process of computing the eigenvalues, you also compute the eigenvectors. And the eigenvectors are not unique, so you have to normalize them. So you normalize them to, so for example, when you try to solve for the eigenvectors of this, it might turn out that recover this eigenvector. This is an eigenvector. This is also an eigenvector. If I multiply by anything, would be an eigenvector. Especially if I multiply by this, would be an eigenvector. But this has unit norm. In general, once you compute this, you can compute its norm, which is just √2, and then you divide by √2, which gives you this. The fact that these are orthogonal to each other, you don't have to do anything. Once you compute it, they're going to be orthogonal because the eigenvalues are different. This is the same here. So if you have a symmetric matrix, if the eigenvalues are different, the eigenvectors you can prove are going to be orthogonal to each other automatically. The only case that you run into problem is you have the case where, for example, you have repeated eigenvalues. So if it turns out that you have a 3 by 3 matrix and the eigenvalues are 2, 2, 1, then when you try to compute the eigenvectors of 2, you get an entire subspace of 2-dimensional subspace. There's a lot of freedom in choosing these two eigenvectors, and then you can find an orthonormal basis in the subspace. This would be a little bit beyond the scope here, so that would be like a linear algebra topic. So I would say go through your linear algebra notes or a linear algebra course where they discuss driving the eigenvalues like eigenvectors. And once you have the eigenvalues and eigenvectors, you can try to consult this slide. The way that you construct the U and lambda is by just putting the eigenvectors on the columns of U and putting the eigenvalues on the diagonals of lambda. Usually you can recover this. So as an exercise, try to recover these representations. So this is exercise. Does that make sense? I'll try to not ask you to figure out the case of repeated eigenvalues.
Oh, okay, yeah, yeah, makes sense. Thank you.
No problem. Any other questions? Okay. One last point is that these PSD matrices are like positive numbers. I mentioned that they're a little bit different. Things are a little bit more subtle. But they, so matrices that have all the elements non-negative, they're not kind of the matrices that act like positive or not negative numbers. Instead, these matrices are what look like positive numbers or non-negative numbers. In fact, or like as a consequence, you can define a square root for these. So for every positive number, you can define a square root within reals, right? √4, this is 2. Just like that, you can also define a square root for PSD matrices. So a square root, if you remember what it is, what is the definition of a square root from elementary mathematics? What is the square root of 2? How do you define it? What's the definition of a square root?
The number whose value squared is 2.
Yeah, so it's the solution of this equation. If I square x, I should get 2. That's what we call the square root. There are two numbers, so there's like positive or negative √2, but usually we talk about positive square root. So when we talk about the square root, usually we mean the positive one. So the positive solution of this would be the square root. We can say x times x is equal to 2, the number that has this property. So the same goes for a matrix because we have matrix multiplication. A square root of A is a matrix such that when I multiply by itself, it gives me A. In other words, A 1/2, or if you want, root A is a matrix such that when I square it, it would give me A. This or this are the same. It's different notation. And every positive semi-definite matrix has a symmetric square root. So because we're talking about matrices, there are options. Here we require that they be symmetric and also PSD. So A would be PSD as well. So I require, it's like here requiring that the root be itself positive. So every symmetric matrix has such a square root. And an easy way to drive it, if you have the eigenvalue decomposition for the symmetric matrix, if it's positive semi-definite, you know that the diagonal elements are on the lambda are non-negative. So you just take the square root of the diagonal element, you leave u here, and u transpose here intact, and this would give you the square root of A. And the square root of a diagonal matrix is just what you would expect. So if you have a diagonal matrix, the square root would be just, you take the square root of the elements on the diagonal. It's easy to see that this is really a square root. If I multiply it by itself, it gives me back this. And then I let you verify that this is really a square root. So the claim is that this is a square root of a symmetric PSD matrix. In order to verify it, you have to verify that if I multiply it by itself, I get back A. And using the fact that U and lambda are special matrices, you should be able to prove it. Okay, I see that there's some also Josh mentioned what the square root is. Okay, so this makes sense. So we talked about the spectral decomposition and positive semi-definiteness or positive definiteness. These are special classes of symmetric matrices, and they act like non-negative or positive numbers. In particular, we have this square root business, which is useful, as you'll see later. Okay, questions, comments? This concludes our review of linear algebra. So if you don't have questions, we can move on. Last chance to ask questions about these. So the most important thing that we covered, all good, okay, is projection. We'll come back to this. These ideas are also very important, but we're not gonna necessarily, so spectral decomposition and positive semi-definiteness are probably topics that you haven't seen presented like this. So I spent some time on them, and we're gonna see them throughout the course, but not as much as this idea of projection. So I would say try to understand the projection idea, and it would help you later on when we get to regression. Okay, so let's go back. So this concludes the review of linear algebra. Now we move on to, I forgot what chapter of the book it is, but this you can think of as sort of a review of things about random vectors and random matrices. So the topic is vectors and matrices of random variables, or random vectors and random matrices, if you want. And properties like expectations and covariance matrices of these things. So this is still a preliminary chapter. So some of you might have seen some of these ideas, but it's helpful to review or make sure that everyone is on the same page. So did anyone get a chance to go over these slides and lecture videos? So I'm gonna be a little bit, let's say, I'm not gonna go into a lot of details here because the videos are more detailed, and these are sort of, I'm just gonna briefly mention some of the key points, and later on we'll use these. You get used to it when you try to use them in our problems. So essentially, this is part of, let's say, 100B, but usually you don't work with vectors there. So So what we want to talk about is, so everyone knows what a random variable is, right? What is a random variable? Anyone? Maybe I had high hopes, or everyone knows what a random variable is. How many people know what a random variable is? Yes. One person knows about random variable. Yeah, usually I just mention this first because. So let's say, what is an expectation? So I suppose you know what a random variable is. So it's just a formal way of defining a random number. Okay, so there is like a little bit of rigor that requires you to sort of connect the probability space to random numbers. There are functions on the probability space that map the like the sample space to real numbers. But I assume that like intuitively you know what it is. When I say X is a random variable, it's just a random number. It has a distribution, which gives you what is the probability that A belongs to an event or a set. So for example, so intuitively X in R, so X is a random variable, means that X is a random real number. There's a more formal definition, but we're not going to worry about that. And so X has a distribution, which means that, for example, I can figure out what is the probability that X is in a given interval. So the distribution determines what these probabilities are. Usually write this as an integral against a density. So if the random variable is continuous, there's a density, I can integrate it from A to B, that gives me the probability. But there are other ways of specifying it. It could be that X is discrete. So I might specify what like discrete values X take. So sometimes this is called the PMF, this is PDF, probability mass function. I hope these things are sort of clear. There are some distinctions in dealing with this, but a distribution basically tells you how to assign probability to events like this. What is the chance that X is an interval? Or from this, using probability tools, you can figure out what is, for example, what is the chance that X is in -1 and 1, and not and, let's say, or X is bigger than 5, let's say. All of this can be determined once you have a distribution. And once you have, so this is related to the idea of distribution. And then every random variable has an expectation, a variance, and other sort of quantities associated with it. So one question is, what is an expectation? What is the expectation of a random variable? How many people know what the expectation is?
Do you want the definition or the intuition?
Both, let's say.
Okay, so for a discrete random variable, the expectation would be the sum over the individual values multiplied by their corresponding probabilities.
Right. So suppose X takes value, let's say A, B, C, with probability, let's say P1, P2, P3. So what will be the expectation of X?
A times P1 plus B times P2 plus C times P3.
Right. So you take the values times the probabilities and add them up. Plus C times P3. In general, you could say expectation of X is like, if it takes values, I don't know, AI with probabilities Pi, I from 1 to K, then that would be, so values, these are probabilities. And so that's the definition of expectation. Okay, so what is the intuition?
So the intuition is, the random variable takes random values. If you were to do that a lot of times, then the expectation would be the average value, or the average value as the amount of times approaches infinity will be the expectation.
Yeah, that's great. So this expectation is, so suppose I have so I flip a coin. The easiest way to do it is by the coin. I have a coin. X is, say, Bernoulli 1/2. This means that X takes values 1 with probability 1/2, and then 0 with probability 1/2. So what is the expectation of X using that formula? 1/2 times 1 plus 0 times 1/2, so it'll be 1/2, right? So one issue is that I will never observe 1/2, right? So this is the expected value, the value that you expect based on the terminology. But you never expect to observe 1/2. You either observe 0 or 1. The question is that why they call this the expected value, and it's exactly because of what Matthias said. Do you know what the name of the idea that you used? So there's a name. So there's some resulting probability that tells you.
Yeah, law of large numbers.
Yeah. So this is the expectation makes sense actually because of this law of large numbers. Yeah, thank you. Josh also made it made the correct call. So law of large numbers. So what this is saying is that for a single random variable, it doesn't make sense. So just if you do it once, you either observe 1 or 0. But if I have multiple of these, let's say n, sample size n from this, if you repeat the experiment many, many times, and then you form the average, sample average, this is going to converge. This is the law of large numbers, converges in probability, or almost surely. This is, hopefully you've seen it at some point, converges in some sense to the expected value of that x. So 1/2 in this case. So you repeat the experiment many times. These are independent, identically distributed samples from the same distribution as x, and you form their average. Now the average can take any values. So let's say you observe 100 zeros and ones, and then you average them. It can't take any values, but you can imagine as n grows, the range of the values, possible values, gets bigger. So you can get, like, if you have 100, you can get 1 over 100, 0 over 100, anywhere, any of these numbers, right? Up to 100 over 100. So you can get fractional numbers. In particular, you can get 50 over 100. So in general, when you do it, you don't get 1/2, but you get something close. And the law of large number is that as the number grows, with high probability, or probability 1, the sequence approaches 1/2. So this is the meaning of the expected value. This is sometimes called the frequentist interpretation of probability. So frequentist interpretation. What do we mean by the probability that something happens, or the expected value of some random variable? We mean that if you repeat it many times, that's the probability with the fraction of times that you observe something. The expectation would be the average value that they observe. So these make sense when you do things frequently, not just a single single trial wouldn't do it. So does that make sense to people? This is just to remind you what an expectation is, right? Questions? Okay, Good. And then you can, there's a similar definition for continuous random variables. You just have an integral against the density. So I'll let you review this for yourself. It's easiest to see in the discrete case. But it's important for us because it tells you what happens on average, and statisticians care about what happens on average. We don't care about a specific case usually. We care about the aggregate or the average. Statistics sort of is the science of what happens on average usually. Okay, so once you realize what an expectation, or you remember what it is, we can define, or what a random variable is, we can define a random vector. A random vector is just a vector containing random variables. So it's just a convenient way of organizing a bunch of random variables. I put them in a vector. Each one of these guys is a random variable. The result is going to be a random vector. It's just a simple extension. And then I can define the expectation of this. So when I write something like this, I really mean something like this. If you want, it's just usually our vectors are column vectors, or they don't have an orientation, but it's easier to write it in this way to save a space. So Y is a random vector. The expectation is just defined as a vector that contains the expectation of the coordinates. So you just apply the expectation to every coordinate. So this is random. This is non-random. It's just another vector of the same dimension, but contains all the expectations. Another way of writing it is, this is a vector. The ith coordinate of this is just the expectation of the ith coordinate of yi. So this is a compact way of writing the same thing. Okay, does that make sense to people? So there's this property of expectation that, let's say if I have, is a very important property. It follows from the definition, but you're not going to prove it. Linearity of expectation. So that what it tells you is that if I have random variable x and random variable y, and if I form a linear combination with constant coefficients, so alpha and beta are constant, non-random. And if I ask what is the expectation of this random variable, what you can do is figure out what are the values that this takes with what probabilities each and use the definition. But once you do it, you realize that this is equal to, I can expand it over, or distribute it basically over the sum. So I get the expectation of alpha x plus expectation of beta y. I can split it over the summation basically, and then I can pull out the constants. So you can write from this, you can just write it this way. So you can pull out the constants and break the sum up, and then just, if you know the expectation of these two, then you know the expectation of any linear combination. So this generalizes to, if I have a bunch of random variables, so these are RVs, these are constants, the expectation of this is summation comes out, coefficients come out, and the expectation moves in. This is the general idea. Okay, so this needs a proof, but either you've seen it before, or I encourage you to try to justify this for yourself. Sounds good? Okay, it's easiest to see in the discrete case, but try to argue it for like the case of two random variables, let's say. Each take like 2, 3 values, and you see why this is true. And so if you extend this, because let's say matrix multiplication is nothing but these linear combinations, there's just this nice extension. So if I have a bunch of these linear combinations, put them together, I can write it as a matrix times vector operation. So if I have a non-random matrix A and a random vector Y, that's a dimensions match. So this matches this so that A times Y makes sense. So this would be a vector in Rm. So this is another random vector whose elements are just linear combinations of Y with different coefficients. And so I can apply that, combine this idea of linearity of expectation with the definition here. And you arrive at this nice idea that I can basically pull this A out. I pull the A out from here from, let's say, the left, and then multiply it by the expectation of Y. Here's a formal proof, but I encourage you to just argue it for yourself. It's just nothing but this idea of linearity of expectation plus this definition of expectation of a random vector. And you have to pull A out from this side. You can pull it from the other side. You can write it like that because matrix multiplication are sensitive to the order of the variables. So you have to multiply them in the same order, that they appear here. Okay, this is not the case. Does this make sense to people? Yeah, so it's a simple idea. This can be generalized to matrices. So instead of a random vector, I can have a random matrix. A random matrix is nothing but a matrix of random variables. So each coordinate, so if you have A, you could like A11, A12, A21, A22, all of these coordinates can be random variables. So this is a random matrix. It has an expectation. So what is the expectation? It's just what you would expect. So you put the expectation in front of every element. That gives you a deterministic matrix, which is the expectation of A, just like we did for the vectors. Here's an example. You can go through it for yourself. It's just not that interesting. And there is an extension of this result, which is stated here. So if I have three matrices A, B, and C, let's say A is random, B and C are non-random. And then I form this matrix multiplication. So this quantity is the random one here. B and C are non-random. We are assuming that the dimensions are such that B times A times C makes sense. So it's a matrix product. Then I can pull B and C out. They're like constants, they move out. And I can apply A expectation to the element which is random, this guy. So this side is non-random. Both sides are non-random, but this gives you a way of computing the expectation of this based on the expectation of A. Again, you can verify this for yourself. Just write down every element. Every element would be a linear combination of the elements of A. And then the expectation moves past everything. And then you can put them back together like this. Again, the order matters here because matrix multiplication is non-commutative, which means just that the order matters. I can't commute the elements. I can't flip the elements around. Okay, questions? A in R? No, so A is a matrix. This is like, suppose I have a 2 by 2 matrix times a 2 by 3 matrix times a 3 by 1 matrix, which could be a vector or anything. So this would be C, this would be A, this would be B. Let me do it like this. So 2 by 2, 2 by 3, 3 by 1, could be anything. But this makes sense. So this is 2 by 2, 2 by 3, 3 by 1. The result is 2 by 1. Right? Once you multiply everything out, you get 2 by 1. So what this is saying is that this is going to be a random vector because this guy is random. This is going to be random. So when I take the expectation on both sides, I want to compute the expectation of this random vector. I can just move the expectation inside, take the expectation here, and then multiply out everything. That's what it means. Okay, no problem. Seems like it was resolved. We'll see an example. There's an example here. Again, it's not interesting. I work it out in one of the lecture videos, maybe 2020, but we'll see a more interesting example shortly. It's just that this is a consequence of linearity of expectation. So you understand consequence of the linearity of expectation. Okay, so questions, comments? So what interesting quantity besides the expectation a random variable has or is associated with a random variable? It has, yes, variance. Okay, so what is the variance? Let's go back here. The concept of a variance. What is the variance?
Some measure of how much the random variable normally deviates from the mean.
Okay, so yeah, a measure of deviation, let's say. Deviation from the mean. Mean here being just another word for expectation. So yeah, so they have sort of, when you say expectation or expected value, we have this in like the law of large number interpretation or frequentist interpretation of expectation. Another name for it is the mean. Usually when they say there is some sort of relation to this, but it also sort of just reminds or brings to mind another meaning of expectation. So an expectation is sort of the center or mean of the distribution. So if I have, so you know the distribution. So now we're like gonna represent things by densities, the continuous case. It's a little bit more visually appealing to work with continuous variables when you try to plot these. So suppose I have a variable, random variable, trying to do something non-symmetric, which is hard. Okay, so suppose you have a random variable, this has this PDF, probability mass function, that F here, the F here. So what this means is that if I want to find the probability that a random variable is in a given interval, I'm gonna integrate this guy. Or in other words, the mass on that interval, assigned to that interval, or below this curve on that interval is the probability. If you look at that representation of, so this is a representation of a distribution of a random variable, then the mean is usually the center. So it's like somewhere here. So once you take, it's like the average location what is the average location of the random value on the real line. So is it going to be here or here? No, it's just like the weighted average. So each position you weighted by the mass, which is like the amount that's on top of it. The mass that's on top of this, you weight this value with the mass, this value with this mass, and this weighted average would give you the mean. So that's the expected value. But there is some sort of a spread. So you have some distribution like this. Another distribution could be very concentrated. The mean could be the same, but it could be very concentrated near the mean. Another one could have the same mean, but very spread out. They spread out. Okay, so the expectation just gives you the mean gives you the location of the center of the distribution. It doesn't tell you how spread out you are. So the variance tells you how, let's say how spread out the distribution, a measure of how things are spread around the distribution. So here has low variance. This has high variance. So what is the formal definition? Like, what is the formula for it? Okay, so this is equivalent. So expectation of x squared minus, this is the second moment, minus the expectation of x squared, which is the first moment. So here x squared is inside the expectation, here is outside. So this is just the mean. Sometimes we can just mu for the expectation. But this is usually not the definition. So what is, you can take it as a definition, it's equivalent, but there's another formula which is usually used. Yeah, okay, so expectation, so variance is the expected expectation of this deviation is squared. So you take x minus the expectation of x. So for every value here, so if x is here, the distance to the mean, that's the deviation here, right? So this distance is x minus expectation of x. It could be on the other side, it would be negative x minus expectation of x. And then you square it, and then you take the average. So it's the average or the mean squared, let's say, distance to the mean. Average or mean squared, you can call it deviation or something like that. If you expand this, it turns out to be exactly equal to this. So this is another alternative formula. But this version shows you, you're actually looking at how much we are deviating from the mean on average. So does that make sense? And this is the square. There's like the standard deviation, which is on the scale or the units of x, which is just the root of variance of x. You take this and then take the square root. This would be on the same scale as x. So hopefully you all know about these things, right? Everyone remembers what the variance, standard deviations, these things are? Yeah. So now how do we define this? So we define things like expectation. It was easy to define it for random vectors and even random matrices. Now I want to define the concept of a variance for a random vector. How do you think we should do it? There's a natural way. Sorry, can you repeat? Yeah. So we define the expectation for a random vector. We want to do the same thing, the equivalent of it for the random vector. So how can I extend the definition of the variance to a random vector? Suppose I have a random vector, y1 up to yn. I want to somehow define a notion of a variance of y. What can we do here? Covariance matrix. Yeah, so you guys know where I'm going, but if you don't know about it, what is the natural way to do here? Like, what is the natural thing to do here? If you want to follow this example, it seems like the natural thing to do is just to take the variances of these things, right? Yeah, just compute a variance for each element and put it here. So this is fine. We can define it like this, but it turns out that this is not the right quantity to work with. It's perfectly fine to define the variance of a vector like that. It turns out that a lot of other nice things can be derived if you define the variance of x as a matrix rather than a vector. So although y is a vector, let this be a matrix that tells you also about the covariation of the elements. So not only how much y is spread out, but how, let's say, the elements of y covary. And that sort of gets you the idea of the covariance matrix. I usually write it as the cov y, but some people write it as variance of y. So usually you don't define it, not how it is usually defined. So this matrix would have the property that the diagonal elements are these variants. So it already contains that information. This is not how it's defined. Okay. The diagonals are those things, but there's more information in this matrix. And you would hopefully understand later on why we define it like this. So the other elements are just the covariances. So the ith element would be the covariance of yi and yj. So if you look at a matrix whose ith element is the covariance of yi and yj, that would be what we usually use as the variance, equivalent of the variance for a random vector. I usually write it as cov y. Some people write it as var y. So for a 2x2 vector, cov or variance, so this would be cov y1 y1, cov y1 y2, cov y2 y1, cov y2 y2. This is just the variance of y1, and this is the variance of y2. And the covariance, hopefully you remember, covariance of two random variables is something which is similar to the variance, but it's you look at the deviations of x, but multiply it by the deviation of y. If you do it for the same vector, you get the variance. But this is for two random variables. So you measure the covariation, how much they vary together. So if this, whenever this is large, this is also large, then the covariance would be large. But whenever this is, let's say, small, this is large, or whenever this is large, this is small, the covariance would not be that big. So it measures how much they sort of relate to each other rather than the spread. It's also related to the spread. So for example, if the correlation sort of takes the spread out, but this is going to be large if the spread is, like, the variances are large and also they covary. So it's a joint measure of the spread and covariation. So that's how you define the variance or covariance of a random vector. We'll see why this is interesting. Okay, so question, how would it be calculated with real numbers? How would it be calculated with real numbers? I'm not sure if I understand the question, but let's say, how do you calculate the variance? If you tell me how you calculate the variance, I can tell you how you calculate the. How do we calculate the variance. So to calculate the variance, maybe you want to tell me. You need to be able to calculate these expectations. If you want to calculate these expectations, you need to have the distribution of x. Just like, for example, the thing that we did here. So you need to know the distribution, something like that. Then you can compute the variance, and then you can compute the covariance. So for you to be able to compute the let's say a covariance matrix like this, anyone knows what we need, what information we need here to be able to compute this matrix? If I know the distribution of y1, I can compute the variance. If I know the distribution of y2, I can compute the variance of y2. But how do I compute, for example, something like this? How do you compute the covariance of y1 and y2? Yeah, so you need the distribution of, right, you need the distribution of, let's say, yeah, so if you look at this, if I have the distribution of this guy, then I can compute the expectation. Yes, how do you get the distribution of that? Anyone? Because we are out of time, so everything sort of follows if you know the distribution of x, y jointly. In this case, for example, if you know the joint distribution of y1 and y2. So this is like the joint PDF. Then you can compute everything because you know you don't need to compute actually the. For example, this needs the joint distribution of x and y. You don't need to compute the distribution of this. Once you have this, you can compute this guy a little bit more directly. However, to go back to your answer, usually we're not gonna, you will see examples. How do we actually compute these? Formally, you need the joint distribution. Then these expectations are integrals, and you can compute the integrals. Or there's summations, you can compute the summations. You just have to, if this is going back to the bare, let's say the principle based on the definitions. But in practice, in this course at least, you will see what we are going to do is that we are going to reduce the computation of this to computation of simpler things. So we're going to use properties, just like, for example, this property that I mentioned. If you know the expectation of y, you can compute the expectation of a times y. We're going to use these tools to be able to reduce the computation of the covariance matrix to something simpler. But if you guys are interested, I can assign you homework problems to compute it from the actual distribution to remember. So if you want to compute these in the actual setting, you have to go back to 100B. So for example, you're given a joint distribution for, sometimes they give you a joint density of x and y. Okay, and then once you have this, you can compute a lot of things. In particular, if you give me the joint density of x and y, then how do I compute, for example, expectation of xy? Anyone knows how to compute this? So you can show that the covariance of x and y is the expectation of xy minus expectation of x times expectation of y. So you know how to compute the expectation of x and y, let's say from the densities. You need to compute the expectation of xy. So how do you compute this?
And it's the same way as before. It's like if the discrete sum of then xy times.
Right. Let's say
continuous-
they're not discrete. They're continuous to have like a
Okay.
variation.
Well then, oh yeah, okay. Well then, continuous xy times joint probability mass function.
Yeah, so this would be density
Sorry,
equivalent. So this
integral,
is like
yeah,
the
integral.
probability. So integrate xy times the density, joint density.
Yeah.
So that's how you compute this. Expectation of x you can also compute would be like f of xy. This is dx dy. You can take dx dy, or you can just do it with the marginal dx. Same goes for expectation of y. So you have these numbers, you plug it in. Okay. This is not what we're gonna do most often in this course, but this is like 100B. At first, this is the basic. This is how you can always do it. You need to know the joint, something about the joint distribution. If you have it, then for y1 and y2, you can compute all the elements. These two elements will be the same. You have to basically compute 3 elements. So let me, I don't know if I answered that question. It's a little bit abstract at this point, but let me come back next time and talk about the properties, and you'll see some examples of how we do it. Okay. Sounds good? Questions, comments? Okay, feel free to ask questions. I'm going to stop recording.